to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's us. Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe and also a friend to my co-host.
I'm Connie. I am a curious co-host and Moiya's friend and the universe's friend and hopefully all of your friends.
Oh, yay. Friendship all around.
Indeed.
Well, how are you feeling like a close friend to the universe this week?
You know what? No. Because I want to go outside and water my plants. I need to do some plant care. I need to take care of the earth, or at least the earth that I have gathered and collected for my patio. And so I will aim to feel closer to the universe and to my plant babies soon.
Oh, I love your plant babies because some of your plant babies are my plant grandbabies.
Yes, indeed. Indeed.
I am not feeling very close to the universe this week because what business does it have being this cold? I just don't appreciate that because the universe didn't have to make the rules of thermodynamics such that less incident flux from the sun made me shiver like this. Like the universe could have made those rules a lot nicer for me personally.
Right. Yeah, just okay, so here's the science question. If we moved the planet could we move Earth into a minimal left turn and would it make it warmer? Like if we just moved it like a meter or like 5 feet or like to make it still livable. How wide is the zone, I guess?
Very interesting question. So, Bestie, a lot of people think that the seasons are caused by Earth moving closer to the sun and farther away. And they're when it's closer to the sun, then it's summer.
Right.
But that's not true because then the hemispheres wouldn't have different seasons. Yes, exactly. It's the axial tilt that gives us the seasons. And in fact, when the northern hemisphere is experiencing winter, we are closer to the sun than when the northern hemisphere experiences summer. And the difference between what we call apohelion and perihelion, or furthest from the sun and closest to the sun, that difference is about 5 million miles.
So basically, no.
That was a long way of saying no, yes. But I needed you to understand why no.
No, it was a helpful way of saying no because, yes, there was I did know it was the tilt and not the distance. And so I had to be reminded of that. But also, and then I thought about it and I was like, yeah, but even if you adjusted the tilt, it would just be half the planet.
No, the tilt would actually make it much better.
Then that's what we should do. Okay.
Yes. Yeah. If we had zero axial tilt, then we wouldn't really have seasons at all. And all of the latitudes would just kind of keep the same weather year round based on the incident flux that they always have. But even the poles, if we had zero axial tilt, the poles wouldn't have that whole the time of the year where it's always night.
Right.
Or the time of the year where it's always day. They would experience the shift.
Right. But would it be summer all the time?
No, we wouldn't have seasons. It would be the same weather year round.
Yeah.
There might be a slight difference because of that 5 million miles. Technically, the southern hemisphere does have a less extreme winter, but that's more because the southern hemisphere is more covered in water than the northern hemisphere, which is more covered in land. So there are just so many factors.
Right.
I think we would just stop having seasons altogether, and we'd all be living in San Francisco. Or LA.
Okay, so that's what I also wanted to know. Is what temperature would it be all the time? And that is what my preferred temperature would be. But I know that it's not everybody's choice. Some people
It would depend on your latitude. If we had zero axial tilt, then the sun would shine directly on the equator all year long.
Right.
But if the Earth continued to rotate, then the equator would still experience night and day. And we would all have 12 hours of day and 12 hours of night as the Earth rotated. But the higher latitudes, the more extreme latitudes further away from the equator, they are getting less direct sunlight. The sunlight is coming in at them on an angle, much like it is for any hemisphere currently experiencing winter.
Right. Okay.
Yeah, so it's the extreme latitudes would be in winter and the equator would be in summer, and then things would shift accordingly
Between
between them.
them. Huh.
What a fun way to start the episode.
Yeah,
that's not even what we're talking about today.
Now I feel closer to the universe than I did 5 minutes ago, so it's great.
Good. Love that. So today we're talking about a Greek astronomer and mathematician named Hipparchus, and this was another topic nearly requested by Connie. Connie, what did you actually want to learn about?
I forgot.
You forgot? It was the magnitude system.
Yes.
Of how we determine stellar brightness.
Yes, brightness. And Moiya said, so I can tell you about Hipparchus. And I was like, sure. And then I forgot that those two things connected because I don't have a strong association of Hipparchus with anything yet.
Yeah.
But I'm about to learn.
You're about to learn. That's exactly what these episodes are for. I do want to start with a quiz, a very chill quiz, and there's no consequences. So, Connie, which of the following fields did Hipparchus not revolutionize? Was it A, astronomy, B, chemistry, C, trigonometry, or D, geography?
Okay. So my guess is that he did revolutionize astronomy because otherwise, why would he be here?
Yes.
I'm going to come back to chemistry. Trigonometry, I'm going to say he did because, one, there's always a guy named Hipparchus or Hypothesis or Hyperion involved in math. So, there's a lot of math stuff involved in that. So I'm going to assume that. But also because space is angles and shapes, it's not primarily what it is, but it's a lot of what it is.
That's a lot of what it is.
Yeah, it's why I didn't study it any further than I did, because suddenly there was a lot of math and shapes. So now I'm left with geography and chemistry. And chemistry, there's a lot of chemistry stuff happening in space because it's also happening here because it's happening everywhere. But geography is too earthbound. So I'm going to say he had nothing to do with geography.
Okay. He, to my knowledge, had nothing to do with chemistry. What? And I'm glad I tricked you because, he was from a time when people just be dabbling.
Yeah,
people would be like, today I'm going to look up at space and tomorrow I'm going to turn lead into gold.
They were just
and the day after that I'm going to make the Philosopher's Stone.
They were general thinkers. They thought about everything and some things a lot. And then some things they were like, well, what about that? It's a side mission, a little side quest while I'm doing my main research. They love a side quest back in those olden days.
They did, indeed. And geography was actually less of a side quest than you might expect, although kind of a little bit of a side quest. So you'll learn by the end how he revolutionized astronomy and trig and geography. And to my knowledge, had nothing to do with chemistry or biology. He wasn't one of those people experimenting with stealing corpses and hacking them up to try and learn anatomy. He wasn't one of those.
Right. Although if you should watch Frankenstein if that's what you're into. The new Frankenstein movie if that's what you're into.
There's a new Frankenstein movie?
Oh, yeah. You don't know about this? Oscar Isaac?
Girl, that's not my...
I forgot.
That's not my corner of the internet.
You're right. But
that's not my buckshot.
Yeah, it's Guillermo del Toro directing Oscar Isaac as Dr. Frankenstein, and Jacob Elordi, tall man that he is 6'4".
I know him from Saltburn.
Yeah. I know that he was on Euphoria, but I did not really know about him until Saltburn, and I still haven't seen that one. But it was a lot.
It's not for you, bestie.
He was in the news, is what I'm saying, and so I was aware of his existence more. And then now he's in Frankenstein.
Oh, okay. Yes, if you want to learn about old doctors, just experimenting with anatomy. Yeah, look at that.
And the hubris of man.
Bestie, do you have any questions, or are you too full of the hubris of man?
Okay. I have no questions about Hipparchus except who Hipparchus is.
I'm sorry, but you could never have the same amount of hubris as a man.
I just wasn't born with it.
Yeah. So there's not much known about Hipparchus's personal life. So when you asked who is Hipparchus,
right.
And unfortunately I can really only tell you about his professional life. I don't know what he liked to eat. I don't know if he was married.
He said, I go to work, I show up, I go home.
At least that's what the history books say about him.
Yeah.
Like, we don't even know exactly when he lived. We don't know exactly where he lived.
We just
or when
know
he
it was
died.
somewhere in Greece.
Yeah, so we're pretty sure that he was born in Nicaea, which is modern-day Turkey, around the year 190 BCE. That's our best estimate. And our best estimate for his day of death is around 120 BCE, so he lived to be about 70 years old. The 120 is an even looser estimate because that's just based on when he stopped working, like when he stopped publishing things.
Huh.
He might have died in Rhodes, and that's based purely on the latitude that makes the most sense for his later observations and calculations.
I love that there are people, I mean, it's like, of course, there are people out there who are doing the math on, like, where did this man live because of X, Y, and Z and the latitude of where he was. And it, like, one, it reminds me of, like, Bible, like, research of, like, oh, this is where this probably was because of the sun and the references to, you know, astronomical things. But it's also reminiscent of, like, fan behavior.
Yes.
Where it's just like, oh, I need to know where my fave is. Where is she? Where was she? Oh, I can. Nowadays, we use Instagram. Oh my gosh. In the background of that Instagram post, I see this hotel. So they must be, we've both been on TikTok and seen those guys who, like, try to find out where people are based on, like, their Google Maps. Wild.
Yeah, so people are very interested in trying to eke out as much detail as we can about this person's life. So we think he died in Rhodes and lived there for a long time, but we also know he made some observations in Alexandria. We know that he extensively read Babylonian astronomy to a point where some of his contemporaries and the people who read his work after were like, huh, that's a little weird. Like, he really liked those Babylonians. Like, other scientists who read his work were like, is this the only person that he was referencing? So yeah, he was very influenced by Babylonian astronomy.
He's like, this is what I had. This is what they taught me. I guess we don't really know that much. So it's like, that's what they taught him. So he started there. Maybe, I don't know. That's interesting.
Yeah. And very few of his actual works remain. So most of what we know about his projects actually comes indirectly through not even his students that he, like, directly taught, but people who read his work later. So people like Strabo, who I haven't really heard of, but, like, Ptolemy loved reading Hipparchus's stuff. And a lot of what we see in the Almagest and in some of Ptolemy's other work, he references Hipparchus and uses Hipparchus's catalogs and measurements to do his own work.
Did they then just think maybe we should go look at the Babylonians?
I'm sure they went, or they might not have had access to the text, actually.
Yeah.
Because a lot of things were destroyed over time.
Yeah, it's very curious that his life is so removed. Like, it almost feels intentional, but only because I know 5 minutes of information about it. So,
I mean, that was a chaotic time. Yeah. A lot of information is lost from that time. And he wasn't a king. He wasn't a wealthy person. He was a humble scholar, as far as I know. And so there weren't really, in the present, it didn't seem like there was reason to, write down whatever he was doing.
And then, so his information, he wrote it down, but then is that, like, I'm wondering how, like, Ptolemy got his work. Like, was it just because he worked?
Yeah, he did write it down.
And he worked in the place where they said, he had access. Ptolemy then had access to his writings.
Yeah, yeah. There were fewer copies of manuscripts back then.
So I'm like, oh, he had it.
Yeah.
He had it at least.
Yeah, exactly. Like, Hipparchus did publish. The publisher-parish culture goes very far back. Hipparchus published and perished.
Yeah, and And then they like, okay, here, actually, this is pretty good. Let's keep it in the library. Don't care about who he was, but this book is pretty good.
And then libraries burn down and people get lost. Like I don't think there's some grand conspiracy trying to keep us from learning about Hipparchus's personal life. Yeah. Probably. Although, if Dan Brown wants to write that book, sure.
Yeah.
I'll read it. So I have here basically a list of his professional accomplishments, and he did a lot of stuff. But people back then, they all had to be really talented. So I went to a really small high school, and one thing that people always ask me about life in such a small insulated community is, did you have like the typical high school cliques? Absolutely not.
Correct.
Like, we had basically like 2 or 3 large cliques, and it was the people who did stuff and then the people who didn't do stuff and then the people who only did like farming stuff.
Yes.
But if you did things, you had to do all of the things. So the jocks were also in band and theater and chemistry club. Yeah, you had to be everywhere. And you just were in everywhere,
and you're talking to a lot of different groups of people or around a lot of different groups of people. And it's like, yeah, this basketball player, he's about as likable as the nerd in the corner, but like he's just everywhere.
They're both everywhere because they're both do something kids.
Yes.
Like I was a jock and a band geek and a theater kid and in chemistry club and honor society. Like and the most popular kid in class. I was not popular. I was not. But the most popular kid in class was also in chemistry club and honor society and played football and like all the things. So that's what being a natural philosopher was like in the BCEs. And so
listen, they didn't have scrolling to distract them from all of the things that they could do in life.
It's true. Just demons that they were trying to distract themselves from.
And scrolls, I guess. Actual scrolls.
Yeah. So I'd say the most impressive and influential of his contributions was that Hipparchus produced the first known catalog of stars and their positions. I don't think he developed the latitude-longitude system, but he applied it to the sky and would use tools, some of which he invented, to measure angles above and below the celestial equator. So he would find a star, he would list its position, and then he would also want to list how bright the star was. And so he came up with a system for measuring or at least quantifying a star's brightness. And the legend says that he started making this catalog after a new star appeared in the sky in either 133 or 134 BCE. And that new star would have been like a supernova that went off in the sky and was newly visible. And in order to prove that new stars appeared in the sky, you had to have a list of where all the previous stars were.
Yeah. I can prove it's new because these are the ones that were already there.
Right. Look, the chart says new star, and it had 850 stars in it. I mentioned that he invented a couple of tools to do this position measuring. One was called a diopter. This was a really narrow tube to focus your vision on the sky, but it didn't have any lenses in it, so there was no focus or magnification in the optics sense. It just kind of like made it hard for you to see anything else, so you had to just look at this one narrow field of vision.
Right. That helps with like distraction. Like, I don't need distraction from this other twinkling star. I want this one.
Exactly. And another type of tool that was kind of like an astrolabe that he would use to measure the angles themselves. So I imagine that he would like have this narrow tube and he would put it on the angle machine and then look through until he found the right star and then look at the angle machine to see the position. And in order to write down the brightnesses of these different stars, he looked at the 850 stars in his catalog and he divided them into different groups based on their brightness. He essentially ranked their brightnesses and split them into 6 different classes. And he noticed that the brightest category was about 100 times brighter than the stars in the dimmest category. he called the brightest stars first magnitude and the dimmest stars sixth magnitude stars.
This is somewhat familiar. I forget why I learned this from you before, but now, because there are stars that are brighter than that first magnitude, and you had to come up with a new system or like an additional.
We just went negative.
Right. But then it's the more bright it is, the
more negative it is. Okay. So there are stars that have like negative 27 magnitude.
Huh.
We did reconfigure. So there are a couple different magnitude systems that use a different 0 point, but the most commonly used magnitude system uses the star Vega as the 0 point. So anything brighter than that, like Sirius, is going to be like a negative 2 or something on the brightness scale, and anything dimmer than that will be above a 0. But different systems have that different calibration point. It really trips up a lot of early career astronomers when they're just learning about magnitude systems in their classes. I remember being very confused. Now looking back, I have the intuition and I'm not confused anymore, but it is unnecessarily complicated to have it get dimmer as the numbers go up.
I'm still confused, but it's okay.
Hey friends, it's me. Connie is outside with our supremely long measuring tape, the SLMT, that is its official name in the way of astronomers. She's trying to measure the distance to the moon, so I'm going to let her do that and use the time to share some messages with you. The first message is, of course, a thank you to all of our patrons who support us and Pale Blue Pod every month. We're an independent podcast paying Misha, our editor, out of our pocket. So thank you very much for all the support you can give us. And I want to give a special shout out to my sun-like stars, Scott Reynolds, Tom T, Nicole Bartlett, Ashley Shambo, Mark Mahoney, Bruce Sedloff. Thank you, my golden friends. I appreciate you so much. I hope you're enjoying your yummy fusion snacks. If you want to join this awesome group of people, support an indie podcast, hear your name on the show, make it to the patron star chart, and get research notes for most episodes, you can do that for $5 a month by joining at patreon.com/palebluepod. And we also offer annual memberships. So if you sign up for a whole year up front, you end up getting a 13% discount across the entire year. That's 1% for every constellation in this ecliptic path of the sun across the sky. Of course, if you can't support the show financially, we understand. You're still space and we love you. We would really appreciate it if you could help the show grow by getting more people to listen to it. So if you take this episode link and send it to someone who's always been interested in ancient Greece, or maybe wants to know more about how we can measure the distance to the moon without fancy equipment, they would learn more about the universe, and the universe would gain an extra friend. So thank you in advance. The next message I want to share with you is a podcast recommendation. It's another show in the Multitude Collective, and it's the Other Science Show. It's called Tiny Matters. It's an award-winning podcast about tiny things, from molecules to microbes, that have a big and often surprising impact on society. They're covering everything from deadly diseases to forensic toxicology to the search for extraterrestrial life, which we here will all find very interesting. The hosts are former scientists Dr. Sam Jones and Dr. Deboki Chakravarty, and together they embrace the awe and messiness of science and also its place in history and today, and how it could impact our world's future. So they really give you everything in the show. Tiny Matters is brought to you by the American Chemical Society, a nonprofit scientific organization based in Washington, D.C., and it's a part of Multitude. New episodes come out every Wednesday, so check them out wherever you get your podcasts. It turns out our supremely long measuring tape is actually designed for such large distances that it only works on AU scales. So Connie just measured that the moon is less than 1 astronomical unit away, which we already knew, but that's fine. Let's get back to this conversation about Hipparchus. So part of the standardization of this system happened in 1856 when an Oxford astronomer named Norman Pogson, which I think is one of my favorite names we've had on the pod in a while.
Norman Pogson.
Mm-hmm. Norman Pogson, good old Norman Pogson. He standardized this magnitude scale from Hipparchus because they were starting to observe brighter and dimmer objects as telescopes got better. And so he developed a logarithmic scale. Do you know what that means?
I think so, but also no. So is it like with like 8 and 16 and 64-bit? Like, is it that kind of like a multiplication system?
Yeah, it's related to multiplication systems. It's kind of like the inverse of exponents.
Mm-hmm. Okay.
So if you have an exponent like 10 to the 5th power, 10 to the 5th power is 100,000. If you were to take the log based 10 of 100,000, that is 5. Mm-hmm. So a logarithmic scale is one that kind of takes exponential growth and adjusts it to a more linear scale. And we do this often with log base 10, but you could do log base 3 or like whatever. A natural log is a log with the base e, like e the number, like 2.17 something. So you can have these logs with different bases. And typically in astronomy, we will use a lot of log base 10 so that we can kind of scale down the massive scales that we deal with. So instead of having a chart that goes from like 0 to a million, in the log scale, log base 10, that just goes from 0 to 6.
Gotcha.
So it does squish some things together, and it does morph the perception. It's like when things on maps are distorted when you take 3D and you put it onto a 2D surface.
Yeah.
Things on a log scale are distorted from a linear scale, but it is sometimes easier to understand.
Right.
So what Norman Pogson noticed was that since the brightest stars in Hipparchus's catalog were 100 times brighter than the dimmest stars, that means there's a factor of about 100 times in brightness for every 5 steps of magnitude. And he turned that into a logarithmic equation that makes every magnitude step brighter or dimmer than the next step by about 2.5.
Mm-hmm. Okay.
And that standardization, that equation is really useful because it allows us to take advantage of something called apparent versus absolute magnitude. We know how light disperses over distance. We know that the amount of light you receive from an object is going to fall off with the distance squared. So if the object moves 3 times farther from you, then it will be 9 times dimmer. It will be the distance squared dimmer. So if we know how bright something looks to us, that's its apparent magnitude, and we know how far away it is, then we can calculate its absolute magnitude. So if we have any 2 of those numbers, either its distance, its absolute, or apparent magnitude, then we can calculate the others.
Okay.
There's actually an equation that we learn early on in our astro training called the distance modulus, which is like you can put in either the distance or the apparent or absolute magnitudes and then work out through algebra what the others are.
Oh, so where you only have one, right?
I think you need 2. You need 2 of them.
Two still. Okay.
Yeah. So that's, I think, Hipparchus's biggest accomplishment. Yeah. Another thing he did was calculate the distances between the Earth and the Moon and the Earth and the Sun, although he was much more successful calculating the Earth-Moon distance. Yeah. And he did that during a solar eclipse.
So he was doing like both of those like equations and math at the same time?
I know he did the moon one during the eclipse. I don't remember how he calculated the distance to the sun.
Because I wonder if that was part of
It could have also been with the eclipse, I think.
Yeah, because I was wondering if that was part of his, why? Because it's like, how does the distance work that it completely covers? And so he was like, let's do the math.
Yeah, I think he had another way of calculating the distance to the sun, but he used a solar eclipse and parallax to measure the distance to the moon. Do you remember parallax?
Yeah, it's when it looks like it's moved from one side to the other based on your perception.
Yes.
Great.
Yes. When your perspective, when the angle from which you are observing an object changes, it can look like that object moves compared to the background. And if the object is closer to you, it will look like it's moving more. So there is a limit to the parallax distance method. Mm-hmm. The farther an object is, the smaller its parallax angle will be. So eventually this method becomes useless. But within our solar system, you can actually do it. And he had a really clever way of doing it. So in 129 BCE, there was a total solar eclipse at Hellespont, which is a town in ancient Greece or Egypt or something in the ancient world. So it was total at Hellespont, but in Alexandria, where Hipparchus was observing from, it was a partial solar eclipse. Mm-hmm. Knowing the distance between Hellespont and Alexandria and then measuring how much of the sun, like proportionally, is visible outside the moon's edge in Alexandria where it was partial, that gave them like a parallax cross angle that they could calculate. And Hipparchus calculated that the moon was 60.5 Earth radii away. And when you do out that math, it's about 240,000 miles, which is, yeah, he was like really, really close.
Wow. I feel like I've seen a internet diagram about this on like TikTok or something, probably around one of the eclipses that we've had recently where someone's like, yes, you can do the, and I feel like I remember seeing like, oh, if he was in Greece and this person was in Alexandria, like it just feels very familiar from those like educational, but now increasingly AI like videos about like how stuff works.
Mm-hmm, mm-hmm. I think they were like, in Alexandria, 1/6 or something of the sun's edge is visible. So 1/6 of the sun was the distance that their target had, quote unquote, moved between their differences in perspective. Yeah, so it's like forced parallax because you're not moving, you're just standing in two different places and comparing your observation, but it got them the right answer.
That's also how they've recently been, we've had some flat earthers on YouTube trying to prove the earth is flat, and similar methods prove them wrong.
You might be surprised to learn that I have never gotten any flat earth content on any of my internet algorithms. That might shock you.
They would never. They would never.
You're right, they would never.
The algorithms already know.
They know I would turn my phone off and then never open that app again.
Mm-hmm. Exactly.
Yeah, so they got really close with the moon, but Hipparchus was off on the sun-Earth distance by about a factor of 10. He underestimated it pretty extremely.
He's like, it can't be that far. Yes, sir. Yes, sir, it can.
And part of that was that he was a geocentrist. He believed in Earth at the center of the system, center of the universe, and that the sun orbited around. And so when you're starting from that wrong base of facts, it's going to lead you to, faulty assumptions in your math.
Wow.
I think we've talked about precession before. How the current North Star is Polaris, but because the Earth's axis wobbles, it will be a different star.
Yeah.
He discovered that.
Ah.
Yeah. Maybe not. He maybe wasn't the first person ever, but he's the oldest record that we have of determining this. We call this, the fancy name for it is the precession of the equinox. And
were you there for the precession of the equinox?
Were you there? But are you really a denizen of Earth if you were not there for the precession of the equinox?
We all go to the precession of the equinox. Like, how rudimentary of you to not even show up.
It's the talk of the town.
Yeah, exactly. You must show up with your best celestial wear. We all show up and we observe the stars together. We because in Bridgerton
that actually sounds really nice.
In Bridgerton, they literally went to the balloon. It was the height of the the Enlightenment. One of those eras where they were doing all the science. Can't remember right now. Oh, it's been so long since I've had to learn.
Yeah. I think Bridgerton is what, late 17, early 1800s. So they were, industrialization was not quite there,
not yet. So
but they were post-Enlightenment.
Yes,
so
they're still like interested in like science is an event to go to, and so
yes,
that's really the vibe I was going for. but it must be hoity-toity because it's the precession of the equinox.
Precession, yes. So he was studying the equinoxes because he wanted to be able to accurately predict them. And what he noticed was that it moved very slowly. This wasn't something he like noticed year to year, but very slowly the equinox, the physical location where the sun seemed to dip below the horizon at the moment of equinox, was moving from the east to the west, compared to the distant stars, the fixed stars behind them. He only saw this when he went back into old records from old astronomers, probably Babylonians, if we're being honest.
Yeah.
He went back and saw that it was even further west in old documents. Mm-hmm. So he's like, oh, this is changing. And then he calculated it, and it was accurate. And so then he could accurately predict when and where the equinoxes and solstices would happen going forward. But this is such a slow cycle that it only is complete every 26,000 years.
Oh.
Mm-hmm. So he really wouldn't have noticed it on his own in his own lifetime.
Right, but he looked at the records so far back, yeah.
This is why data archiving is important.
Mm-hmm. Indeed.
Yeah, this is why record keeping is so valuable. This is why I have the utmost respect for archivists. This is why I'm so happy that there were people on the internet just like downloading files from the Library of Congress and other official sites over the last few months.
Yeah, definitely. Yeah. And why it's actually also important to research papers outside of your own culture, because if you look at the Babylonians, you might learn something new that you can then pass down to your Greek counterparts. Don't forget.
I think the takeaway from this episode is we should all be reading more Babylonians.
Yeah.
Anyone want to get together for an Epic of Gilgamesh reading party? Like, let's do it.
I mean, as the folklorist here, I feel like you should be the one leading this charge. Let's go.
Hey, maybe if we get a certain number of patrons, we can organize a star party where we also read and discuss the Epic of Gilgamesh and other ancient tomes.
Let's get that going, folks. Let us know.
Let us know. Okay, so that's the precession of the equinox. His other title that sometimes people use for him is the father of trigonometry. He is said to have founded this mathematical discipline.
I was like, it's somebody with a Hipparchus, Hippolyta, somebody. I knew it was somebody.
Queen of the Amazons, just casually taking some time out of the battle to calculate angles real quick.
That's what The Good Place told us.
That was Hypatia.
Dang it. See?
Who was an astronomer. Yes, so you're not wrong. Hipparchus reportedly wrote a 12-part treatise on chords. I don't think I could fill 12 pages with information on chords, but he wrote 12 whole different books on them.
If there are diagrams,
almost certainly.
Then like if you just have a chord
these have not survived.
So we don't even know.
We don't know. We don't know. We've just heard tell.
So it could have been the first 12 pages were just different lines of different widths or we don't know.
We don't know. But for those of you who aren't familiar with chords, these are lines that cut across a circle.
Yeah, there were definitely diagrams.
And you wrote 12 books on that.
No, there are definitely so many different size circles in that book that just each page was just a circle with some lines across it and some notes.
Yes.
And that's why it took 12 books, because he was like, well, what about this size circle? And it's just a little smaller.
Yeah. Like he really was just deep in thought about angles and lines and circles for years. And he used a lot of that work when he was trying to measure the angles of like the positions of stars and then try to predict where they would be at a certain time. So yeah, trigonometry I can vouch is very important in astronomy. When I got to Harvard for undergrad, I was pretty confident in my calculus ability, but I was actually put in rudimentary math classes because I didn't know enough trigonometry. Okay, in my defense, I went to a really terrible public rural school in Pennsylvania where I know for a fact my teacher actually taught me incorrect math.
Oh, great.
Yeah.
Great.
So I had to start at rudimentary math classes. And for all the people out there who are like, oh, I want to study space or I want to get into science, but I'm not good enough at math. I started in rudimentary, like not even 101 level. They had to take me to like level 1 for math in college, and I still ended up here. So you can truly find a way.
Well, you had to start off with, I felt my calculus skills were pretty good because I didn't even get to proper calculus in my school, which was an Upper East Side public specialized tested in school. I was in rudimentary math and my peers were all in calculus AB or calculus BC or whatever they called them. And I was in intro to calculus with all the other kids who could not do math or calculus very well. So some of us are starting even further behind. But then, see, this is where I am. And I just get to talk to my bestie who knows all the astro stuff. So she can do all the math. And I can look at all the pretty space things and be like, wow, I know a fact about that.
That's how our friendship works.
We need both in this world.
We do.
Yes, and we need both in this world.
Absolutely. I almost didn't become an astro person because of trigonometry. That is how much trig there is in space science. But, SOHHH is now permanently just like etched in my brain.
I don't know. That sounds familiar. What is that?
It's the mnemonic for how you calculate the sine, cosine, and tangent of a triangle. Sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse, and the tangent is the opposite over adjacent.
Whoa, you took me all the way back to my 11th grade math classroom. Or maybe 12th grade, I don't remember.
I saw it happen, yeah. Wow. I saw you regress back to that moment.
Like a reverse Raven?
Yes,
like I'm seeing into the future, I'm seeing into the past.
Yes. It physically knocked you back in your seat.
Yeah. So I was like, why does that sound familiar? Oh, no.
I hope no one has nightmares of SOHHH.
Yeah, hopefully not.
Later.
But probably some freshmen in college, though. So sorry about it for y'all.
Yeah, so he is the father of trigonometry, so we can blame him for all of our nightmares. And to bring in the geography of it, like I said, he didn't invent the latitude-longitude coordinate system, but he did do the practical work of lining up the latitude-longitude system with actual real spaces here on Earth. So he did the math, he did the trigonometry to say, okay, if this is the size of the Earth and we have this coordinate system that goes from, positive 90 to negative 90 north-south, then where is 40? Where is the physical location for that? And that's a very practical application that, we need. So that's like his professional accomplishments. He left behind, obviously, a huge legacy because we're still talking about him and he did all of these amazing things. But there are like actual, concrete things. There's like things named after him is what I'm trying to say. So there is a Hipparchus crater on the moon. So the features on the moon are mostly not named after mythological figures, actually. The moon features are named after real human scientists and artists. And so Hipparchus has a crater on the moon. Nice. He also has a crater on Mars. Sure. I don't remember the naming convention for Mars's features, but clearly it also includes humans.
Real people.
Yeah, real people. There is an asteroid named after him. There's a Hipparchus asteroid. So it's almost like they're just naming everything after him that they can.
Yeah. They're like, we don't know a lot about his personal life, but we going to carry his legacy forward.
And I think the best way that we have carried his legacy forward is with the Hipparchus telescope. This was the precursor to the Gaia spacecraft. It was launched by the European Space Agency in 1989. It operated for almost exactly 4 years and then was retired in August of 1993. And then they, even before it was done, they were planning its successor. which we talked about a couple episodes ago.
We did. Mm-hmm. Incredible. Hipparchus was that guy, a real Renaissance man for his time.
For his time.
His time, pre-Renaissance. But, but reminds me, I guess a lot of these older philosopher types remind me of like Michelangelo, doing lots of different things and being interested in lots of different sciences and philosophies. So, yeah. I don't know. I've been very British this episode. I don't know why.
Yeah. I'm here for it. Keep going. I'm loving it.
Cheerio.
Mate. Okay.
This was a great episode where we learned so much about Hipparchus, and I hope all of our followers and subscribers enjoy learning about Hipparchus and my mixed up accents, because I can feel it on my tongue, the way my tongue is not moving the way it's supposed to. It's moving too familiarly for words that I know would not be as difficult if this were my actual accent.
But you're committed to it. Like you've kept it going. Well, do you have any last words for our listeners?
Pip, pip, and cheerio.
I'm going to say yes. Pip, pip, cheerio. And listeners, remember, no matter how bright a star you are space.
Bye.
Bye.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.